the first term, the time derivative, when integrated over space, right? Actually, the time derivative comes out of the integral directly. So it becomes d dt of the integrated total quantity of u that's inside the interval L to R. And this actually has a direct relationship to what finite volume discretizes. Finite volume, remember, stores the averaged u, averaged solution inside the volume. And the average, the definition, the mathematical definition of an average of a continuous function is what? All right, everybody's muted. I know, like when you guys are in larger classes, it's a good idea to mute yourself. But here, I would actually encourage people to unmute, right? I mean, unless you are in a very noisy environment. If you are in a pretty quiet environment, I would actually encourage you to unmute so that we can actually talk to each other more. How about that?
Okay.
All right. Okay. So here, when we integrate the solution u over a finite interval, right? How does that relate to the way we discretize a function with finite volume? How does it relate to the averaged function within a certain volume?
Isn't the average like when you integrate the function over the interval and divide it by the size of that interval?
Exactly. The average, the mathematical definition of an average, right? So let me write over here. So the average is over an interval L and R is actually defined as 1 over R minus L, the size of the interval, like what you said, the integral from L to R u dx. And because the length of the interval is fixed, when we take the derivative of an integral, it is actually equal to the size of the interval times the derivative of the average. So this directly relates to finite volume itself, the idea of finite volume. Okay, so that's integration of the time derivative term. Now we come to our second term. We are integrating a constant times a spatial derivative. What does that turn into? What happens when we integrate over space a spatial derivative? Yeah, what happens when we integrate a spatial derivative in space?
You get a volume. The space, I mean.
We get a what?
A volume.
Oh, when we integrate the function 1, I mean, when we integrate a constant 1 in space, we usually get the volume, get the size of the space, right? But when we integrate the derivative of a function in space, we actually get what?
The function.
Yeah, we get the function itself, right? We know that when we differentiate an integral, we get the function. Or when we integrate the derivative of the function, we also get the function itself. So derivative and integral is like the inverse operator of each other, right? That's the fundamental theorem of calculus. So basically, when we integrate the derivative over a certain interval, what we get is, of course, we have the a, which can come out of the integral, and times u. Here, I want to put a notation here. The notation I'm going to be using is we have a vertical line with a superscript r and lower script l. Have you guys seen this notation before?
Yes.
Yeah.
Okay, good.
Yeah.
That's the difference of the value of the function between the u at r and u at l, right? So this is basically the difference, and that's the result of integrating a derivative over space. Now comes something we haven't seen before. When we integrate a second order derivative, of course the kappa also comes out, right? The remaining is going to be integral over a second order derivative. Now, what is the integral of a second order derivative? This is going to be
First order.
yeah, the first order derivative. Thank you. I like that. So basically, a second order derivative is the derivative of a derivative, right? It's the derivative, it's the spatial derivative of du dx. So when we integrate it once, we get du dx. We get the first order derivative. Again, it's the difference between the du dx at r and du dx at l. Okay? So what we have is, let me transform the left-hand side a little bit more. So this is ddt of, we have r minus l here, times ddt of u bar, u averaged within the interval L and R. So that's actually what we use to discretize a function. Plus A times U at LR equal to kappa du dx LR. So that's the result of the finite volume discretization, okay? And because we have the averaged value over the intervals, but we don't have even the value of the function at the interfaces. So let's say here is L and here is R, right? We only have the average values. So we have to approximate the value of the function at the interfaces. We also have to approximate the derivative of the function at the interfaces if we have a second order derivative in the differential equation itself. Okay, so all finite volume is doing is basically approximating, approximating basically what we call the flux at the interfaces between these finite volumes. All right, so last lecture we have learned that, for example, if we denote